these things.
You know, pretty soon it's going to be 12, 12, 12.
It is. Alright, everybody. Welcome to biology class. Happy Monday.
Hi.
I'm Mr. Auerbach. Are we ready? Alright, so what do I got here? I've got, if we were to classify these as a subatomic particle.
Protons.
Protons, right. They're protons because they're positive. And there's two of them. And if I was going to place if I was going to take my orange marker and I was going to place an electron, a single electron, and let's just say I just threw it. Where would it go?
The electron cloud.
Would it go in the middle?
Well, I would do a figure, right?
Well, let's just say it was going to stand still. If I just threw it, where do you think it might end up?
Next to one of closer to the proton.
Well, why would it end up next to one or the other?
Depending on what one needs it.
Well, let's say they both need it equally. They're both protons with no electrons. What do you think might happen?
Chemical reaction.
What's that?
Chemical reaction.
That's not what I'm going for. You guys are way overthinking this. So I take an electron and I place it, I just sort of throw it towards the, between the two of them. Who gets it?
The positive.
They're both positive.
You know what?
Neutron.
I'll
drop down.
You guys, yeah. Well, okay. And how would that work? Well, it's there's only one. I already got. Well, yeah, I got the best answer so far from an adult, but I wanted to get it from one of you guys. So I just sort of I place it right here and it drops down. Where does it go?
Stays in the middle.
It stays in the middle. Why?
Do they repel each other?
Well, they don't repel each other. These two repel each other, but let's say it stays in the middle. Is that the middle right there?
Yeah.
You guys can see this better than I.
Middle-ish.
Middle-ish. I'll say.
Are we supposed to draw this?
Yeah.
Oh, it's little.
It's little. It's actually not nearly as little as electrons really are. Electrons are really about 2,000 times smaller than protons, even though they have the identically opposite charge. In other words, the minus charge is exactly the same magnitude as the plus charge here. And so, yeah, it's going to sit in the middle. Why is it going to sit in the middle? Because it's equally attracted to both of them. They're both pulling on it, and think of it as like a tug-of-war. Custody battle, where both both of them have just exactly the same quality lawyer, but they have the same charge, they have the same strength, and so it's going to hang in the middle. Now, if I was to say these were atoms, what atom would they be with one proton? What element would they be with just one proton? Not a trick question, not a super trick question. How would we find that out? One proton.
Hydrogen. I don't know.
Hydrogen, right? The atomic number. So, right, atomic number 1's kind of missing up there, but it's hydrogen. Atomic number 1, and so let's say this was two hydrogen atoms. It sort of shows how two hydrogen atoms would share an electron. Remember, we learned about covalent bonding. And how sometimes instead of one atom or another one taking the electron, they both sort of share. Each one shows up with an electron and
Figure 8.
They got a figure 8 here, and then this one also gets shared, and it's one big happy molecule. And that's sort of like the covalent bond between two hydrogens. They both have the same pull on it, and so the electrons sort of spend. It's like shared custody, half the week here, half the week there. It's not really like that exactly. It's more like, half a millisecond here, half a millisecond. It's sort of, the electron moves around pretty fast. So it's sort of like they both have it at the same time. Okay, while you're drawing that, I'm going to add to my drawing here. And when you guys do this on your notes, do this as a separate drawing if you don't mind, underneath the first one.
wait to draw that separately?
Uh-huh. Yeah, this would be your second drawing.
Okay.
Ah,
One, two, three.
there's eight. There's eight. There's 8 total, so I added 7 more. But basically now we're looking at a nucleus that has 8. Okay, you take a minute to draw that and think about. I want you to think about what element that would be. Bless you.
Thank you. Wait, so there's supposed to be 8 inside of that?
That is correct. I believe there are, right?
7.
Yeah. There's 8. I bet you.
How much will you have?
Oh.
Mm-hmm.
So, what element would this be?
8.
Hold on. Oxygen.
Oxygen. Very good. Yes. This would be oxygen, atomic number 8. And so, okay. Now, it used to be that our friend the electron was right in the middle here. I readjusted what the middle is since this one got bigger. And we still have our friend the electron here. But do you think it's going to stay there just like that?
No.
No? What do you think it might do?
Hold on.
Somebody's got this custody battle just changed. Somebody's got much better lawyers on this side. The attraction from this nucleus for that electron is going to be much greater. And this isn't exactly correct chemistry, but more or less, the electron is going to want to be over here a lot more than it wants to be over here. It isn't that there's no attraction. There's still a small attraction over there, but there's a much bigger attraction here. And it turns out this really happens. When hydrogen and oxygen compete for electrons, the electron kind of, it's a little bit attracted. I mean, it doesn't go all the way over here. It's a little bit attracted to the hydrogen. But it's much more attracted to the oxygen. And so this leads to our topic of today, which is what a water molecule really looks like. What I had shown you on, what day was it? Friday was something like this. You've got your hydrogen with its 1 electron, and then you got your oxygen with 2, 3, 4, 5, 6 electrons here. You're going to draw 2, just to let you know, there's going to be 2 of these. One is the, let me write oxygen in here. What I showed you on Friday was that these are going to share. Remember, oxygen needs 2 electrons because it has 6. And so it's going to get 1 from each hydrogen. And then the hydrogen needs 1 electron to be full, so it's going to get 1 from oxygen. And it's just going to... Alright, we talked about this. It goes around. Big, happy, covalent bond.
Figure 3.
Figure 3.
I think I
Figure
did mine
16.
wrong. Oh, just kidding.
I have a hard time stopping doing this. It's kind of hypnotic. I probably should have stopped about 30 seconds ago. But anyway, this is the thing. The reason I showed you this was to let you know that it isn't really like this. If you think about the fact that the oxygen nucleus is attracting the electron much, much more. I know we're into some major geek town here, but this is important. So stay with me. I'm going to draw 1 more water molecule. Yeah, okay.
How many electrons put on
There's 8. There's 6 that the oxygen brings, and 1 that each hydrogen brings. By the way, remember when I told you guys to get a set of colored pencils or something like that? This is why. This would be very helpful for you right now. But anyway, here's the real story. That's the theory, but in reality, here's your hydrogens, here's your oxygen, and what really happens is let's see here. Okay, so here's the hydrogen atom here. Let's start here with this one here. It's going around the oxygen, and that's fine because the electrons are very attracted to the oxygen. And it's time to go on to the hydrogen, and it really wants to, but the thing is, it can't get very far. Why can't it get very far? Because the oxygen is pulling it back. The oxygen, remember, the oxygen is much more attractive to it than the hydrogen, so it can't really even get all the way around. It doesn't go all the way around here like I did in this picture. In reality, it goes much more kind of like that, and then it goes back. And then it's like, oh, hey, hydrogen, I'd like to stay, but I really got to go back to the oxygen. Oh, yeah, there we go. And this is sort of more like how it happens because the electron never really gets all the way around. And this is the reality because of, because of this greater attraction. This is what really goes on. The electron never really makes it very far. And let me show you one other thing that results from this. Where's my purple marker? I like purple for this. Don't forget, what's underneath here is the nucleus of the hydrogen atom with its positive charge. And look what we got, folks. We've got exposed protons.
Oh no.
Tell me about it.
That's bad.
Ah! God!
Did you?
Ah!
He did.
I did! Another shirt ruined!
No.
What? No?
What you do is you take a piece of paper towel, get it
Use
wet, and
grease
start
lightning.
dabbing it.
Now hurry
but-
up.
Or
Order
put
dries.
like hand sanitizer
Okay.
and then a napkin on the back of it.
Yeah,
Ooh, you know what I got?
Don't
What about
swipe
that?
it, dab it.
Tide
That
sense.
works.
I needed one of those one day.
That's what I'm talking about.
One time I
What?
got chocolate on my website.
I do.
Oh, well,
That's really going to work?
Leaked out.
yes, it's
Yes,
bad.
what'd you think it was in there for?
Oh, my wife gave it to me.
Oh, me!
Actually, no. I got this for myself. I've just never used it. Do I have to do it from the other side, too?
Say
They don't
here.
do-
Here we are on film.
Got that too.
Got that going for me. Thank you.
First I
Had
started
it
talking
in
about
the
someone
desk
that's
and I never
really
used
crazy.
it.
Okay, we'll edit this part out.
I remember that too.
Menard,
Oh yeah.
We're idiots.
no, leave it in. You deserve it. For having Tide out and you didn't use it. Oh.
This could be on like a Tide stand stick commercial.
Except that it didn't come out.
That's
It did a little bit. Well, it's dry erase. Maybe I should just use the eraser. Just kidding. Just kidding. I'm not gonna do that. All right, you guys, come back to me. I'm sorry. That was my fault. Come back. Where were we? We were here.
We have an exposed probe.
We have exposed protons, everybody. Let me tell you, it's not comfortable. Oops. I'll edit that out too. So here's the thing. These electrons stay over here most of the time, and this is the point. So I need you, everybody, with me here, okay?
Yeah. I'm with you.
The exposed protons. Now we don't just have a neutral molecule like this, where you have totally even distribution of charge. We now have what's called a separation of charge, because these protons are exposed, and the electrons, which are negative, don't forget, they're over here most of the time. So you end up with this electron-rich area here that's kind of negatively charged, and you end up with this area over here that's kind of positively charged. And so all of a sudden, it's not just a neutral thing like a marble that they can bounce off each other and nothing happens, because now it becomes kind of like a magnet. I'm going to erase this part just so I can write. And it's what we call a polar molecule. Why would we call it polar? Question to you.
Cool.
What?
Because it's cold.
Ah, no. Because it's cool. Oh, no. I know you said cold, but anyway, no. Why would we call it polar?
Because it's from the South Pole.
Why do we call the North and South Pole poles?
Because they have poles.
Ends?
Because they have poles. No. Because they're ends. They're opposites. What did you say?
This is not real. It doesn't live there.
Wait, what?
Do they really have...
Hey, guys.
Sorry,
I don't want anybody to end up crying, so let's not talk about the North Pole and you know who and you know what. I don't want to ruin it.
Yes, sir, I'm
You really think that we bring this in?
I just ruined it for him, so it's okay.
Oh
Yeah.
my God. If you need to go talk to your counselor,
I think I meant.
your counselor really does exist. All right, you guys, it's polar because we've got two ends, North Pole, South Pole, like the poles of a magnet, right? And so the thing is, and this is what we have to understand, and we're basically that's almost it. But if we have a magnet, right? Magnet has a North Pole and a South Pole, and that means that it's going to interact with other magnets, and that's what we have to learn. So it's a polar molecule. The only other thing is that its opposite would be like this hydrogen atom that we had before. Whoops. The hydrogen molecule, excuse me, where there was a totally equal sharing of electrons because each one has an exact same pole. So an H2 molecule really does have no separation between the two sides. And there really is an equal charge, and this would be what we would call a non-polar molecule. That's pretty much it, except that now I want to give you a little something to play with. I'm going to give you some water molecules. Here we go.
Well, can I go to the bathroom?
Can you wait 5 minutes? You can wait 5 minutes. Can you wait 5 minutes for me?
I can try.
You can
I'm
try.
at the bathroom.
I can see that you really have to go. I believe you. I just wait a few minutes. Okay. So I'm giving you some water molecules, and on one side it's just paper glued on paper. But if you turn it on the other side, it looks more like a water molecule. It's got the pluses and minuses drawn in for you. Mr. Redmond and I worked very hard for at least 25 minutes making these for you.
Hey, I want some.
Give you some. We got that many. Give you guys some. Here, put your desks together here, or you can sort of look here. You can. Don't hurt yourself. Here you go. Give me a couple. I don't want you to feel left out. Here you go, Alicia.
Thank you.
Yeah. There's some for you. Okay, folks. So here's what I want you to do. Anybody not get any? Did everybody get some? Here's what I want you to do. I want you to think about, now that we know that these have a separation of charge, now that we know that we have a positive end and a negative end of our water molecules, how are they going to interact with each other? If I put two of them next to each other, what are they going to do? Are they going to be like that? What do you think? Do we like this? Are they happy like this?
No.
No. What are they going to want to do?
Go apart.
They're going to want to, well, they're going to repel each other, but probably they'll just flip around so that they're like that. Right? So maybe like on your desk, like just sort of play with them and like however many you have, 5 or 6 or whatever of them, put them in some sort of arrangement like they might sit in real life. So like really, you guys, like go ahead and do that.
I'm different, okay?
What?
Oh, I'm confused.
So you got your plus end, you got your minus end, and you put a bunch of them together with each other. Just try to think about how they might arrange themselves. There's no right or wrong. I'm not checking your answer or anything like that. I want you to visualize it.
Do we need our notebooks open anymore?
You will need to write one more word. Yeah, I'm going to.
What word is that?
I'll tell you when the time comes.
Is it? Well, is the time
And do you know the
You
definition
can go to the
of
bathroom now. Thank you very much for your patience.
Oh. The oxygen.
What are you confused about?
So here's the thing.
We ate.
What's that? You got it. You're pretty good.
I don't.
Well, you don't have it exactly, but let me show you. Let me show you what I'm talking about.
Yes.
Wanted to get this.
Yeah, you might want to reposition that.
Okay.
There we go. Ah, that's all right.
No,
You just need to see this part.
that can't see it.
What?
Reposition yourself then.
No, the recorder can't see it.
Can it?
No.
Now it can.
Oh, thank you. Okay, y'all. So here we've got a water molecule, and you can see the arrows indicating that the electrons are being pulled inward. The pluses indicating that we have a partially positive and partially negative side, which means that this isn't like a full positive or negative charge, not even a full proton or full electron worth of positive or negative charge. It's partial. But it's enough to attract it to each other. And so if I bring another one out here and I drop it, it's going to arrange itself so that the positive side of one is facing the negative side of the other.
Oh,
The hydrogen side of one is facing the oxygen side of the other. This is what we call a hydrogen bond. I'll put another one out there. And another. And another.
Oh,
And another. Look at that. And they actually will.
They make water.
Well, they are water, but okay. So the thing is that they're going to line up like this, and now they don't stay like this because water's a liquid. The molecules are always actually moving in relation to each other, except when? When do they stop moving in relation to each other?
When they're frozen?
When they're frozen. Is that what you said?
Yeah.
Yeah. I thought you said when they're in prison for a second.
I
was
did
like,
too.
but when they're frozen is what? Yes. When they're you can't imprison water. Water is always going to flow out. But anyway, let's not get caught up in whoa.
Unless you think it's frozen as a prison.
That was
You
me
did that.
accidentally.
I thought everything else moved. I thought the whole wall moved. I was like, you're ready to jump. So they do arrange themselves in what's called hydrogen bonds. Most of the time, they're moving, and they just kind of will stop and turn towards each other, and then they'll move on. Except in a few cases, and let me. But when water freezes, it does freeze in exactly this position, except that there would be one more on this side three-dimensionally, and sort of picture another one back behind the screen that you're looking at. But let's look at a real thing, and then we'll basically be good for the day. Here's a lake. I'll show you one thing. We have a pond, and this pond is going to demonstrate a few properties of water that lead from this concept of a polar molecule. And the first one, do you guys see this? You guys see this little water strider sitting up on top of the water? You guys have all seen that, right? You've been to a pond, you see mosquito larvae or water strider or something else. And tomorrow I'm going to show you, we're going to do some activities tomorrow that have to do with these after a little bit of a setup. I'm going to show you tomorrow how you can make a paperclip float on top of water. And it's because of what we call cohesion. The water molecules being attracted to each other can form on the surface of the water what's called surface tension, right? And that, because they're attracted one to the other, it allows them to hold up actual weight. And so we see here the water strider leg, you can see a slight indentation, but it doesn't break what we call the skin of the water. And it's because underneath the water, every once in a while you have water molecules that are attracted to each other, but they move on. On top, there aren't as many forces acting because there's nothing acting from up here, so they tend to line up. And they'll line up one to the other, and they make this surface tension that stuff can actually rest on. And that's called cohesion, together, cohesion, I don't know, sticking. I don't know what the Greek or
Adhesive.
Latin Well, right, like adhesive, except that adhesion is it's related. We're also going to learn about adhesion, so I have to be careful and keep those terms a little bit separate. But yeah, sticking together. Whatever that HESION root is, means to stick together. Adhesion, cohesion. I can't think of another word that uses those. But the point is, water molecules attract each other. They create a surface that stuff can rest on. So, it's not exactly solid like this. In fact, you can break it easily enough if you apply too much force. But anyway, the last thing, Cassie, that I was showing everybody is that surface tension is caused by the cohesion of water molecules. We are in Chapter 4, Section 4. Yes?
So I have a question relevant to this.
Okay. Then I'll keep the camera on.
Yeah, cohesion. There's a dude on America's Got Talent who jumped 30 feet into like a little kiddie pool and did a belly flop. Like, pretty much lived and got up.
Yeah.
Is that because of cohesion?
You know, I assume that it has a lot to do with it. Yeah, I mean, you couldn't do that with a gas, because the molecules aren't close enough to each other to stick. They have too much energy. Water, yeah, as long as you spread out the force, I guess that's part of it. I mean, there's a lot of other physics stuff involved with doing that, but it's sort of the same thing. It's like if you can't really shoot a bullet into water either. But that's a little bit different than this. But this is more like extremely light weights. If the mass is spread out far enough, then they can rest on there. Okay, so would you do me a favor and hit the red button for me there?